Humanity has long wondered if we are truly alone in the universe. With billions of stars and planets stretching across the vast cosmos, the possibility that life exists beyond Earth remains one of our most profound mysteries. Today, scientists are exploring new frontiers in the search for extraterrestrial life, armed with cutting-edge technology and a renewed commitment to uncovering the truth. One of the most promising missions to date is NASA's Europa Clipper, launched on October 14, 2024, from the Kennedy Space Center in Florida. The Clipper is bound for Europa, one of Jupiter's most intriguing moons, where scientists believe a massive ocean lies beneath an icy crust. The mysterious surface of Europa. Europa's surface is a puzzle waiting to be solved. From a distance, the moon appears to be covered in a smooth layer of ice, but as we get closer, we see long, dark lines crisscrossing its surface like cracks on shattered glass. These lines, called linear, are evidence of the immense forces at play. Tidal forces from Jupiter's powerful gravity pull and stretch Europa, causing its icy shell to crack and shift. But what's even more intriguing is what's happening below the ice. Data from previous missions, like the Galileo spacecraft, suggest that there is a massive liquid ocean beneath that icy crust, an ocean potentially twice as large as all of Earth's oceans combined. Why is Europa important? Here's why Europa matters. Where there's water, there could be life. On Earth, we've found life in some of the most extreme environments, places without sunlight, deep under the oceans in hydrothermal vents. These environments are thought to be similar to what could exist on Europa, where heat generated by Jupiter's tidal forces might create underwater volcanoes, providing energy that could support life. Europa is a key to answering one of humanity's oldest questions: are we alone in the universe? If life can exist in such extreme conditions here on Earth, why not on Europa? That's why NASA is sending the Europa Clipper mission to unlock the mysteries hidden beneath the ice and search for signs of life. This tiny moon, just 3,100 kilometers wide, slightly smaller than Earth's moon, may hold answers to the most profound questions about life and our place in the cosmos. Europa isn't just a moon, it's a window into a world that may harbor life unlike anything we've ever known. The science behind the Europa Clipper mission. Now, imagine preparing to explore this distant world, not by foot, but with the most advanced technology humanity has ever created. The Europa Clipper spacecraft. This mission isn't just another routine exploration. It's a high-stakes investigation designed to answer one of science's most profound questions. Could life exist elsewhere in our solar system? The Europa Clipper will launch from Earth and begin its long journey to Europa, carrying with it a suite of scientific instruments designed to unravel the mysteries of this icy moon. What makes this mission so exciting is the technology and strategy being employed to peer through Europa's ice and into its hidden ocean. Instruments on board the Clipper. Europa Clipper is armed with cutting-edge technology. One of the key instruments is ice-penetrating radar. This radar will allow scientists to see beneath the surface and map the thickness of the ice shell. It's crucial to understand how deep the ice goes, as this will tell us a lot about the environment underneath. Are there pockets of water closer to the surface? Or is it a thick layer that shields the ocean far below? Another essential tool is the magnetometer, which will measure Europa's magnetic field. By studying the way this field changes as Europa moves through Jupiter's intense magnetic environment, scientists can confirm the presence of the liquid ocean and estimate its depth and salinity. Imagine being able to sense an ocean hundreds of kilometers deep using just magnetic waves. Hunting for water plumes. One of the most thrilling discoveries from previous missions like Hubble was evidence of water plumes, jets of water vapor shooting out from Europa's surface into space. These plumes may provide a rare opportunity to sample material from Europa's ocean without having to drill through the ice. The Europa Clipper will fly through these plumes if they are present, using its mass spectrometer to analyze the composition of the vapor and search for organic molecules, building blocks of life. If we find evidence of organic molecules in these plumes, it would be a huge step toward confirming that Europa's ocean could harbor life. A multi-flyby mission. Instead of landing on the surface, Europa Clipper will perform multiple flybys, close passes of the moon. each time collecting vast amounts of data. This method allows the spacecraft to gather high-resolution images and measurements without the complexity and risk of landing. Each flyby brings a new opportunity to scan different regions of Europa, offering scientists a detailed look at the Moon's ice surface and the dynamic interactions between the ice and the ocean below. The mission is expected to provide data that will transform our understanding of this moon, much like the Cassini mission did for Saturn's moon Enceladus. Europa, with its hidden ocean, is not just a cold, icy body, it's an active world, teeming with geological processes and perhaps even life. Why this mission matters? The Europa Clipper mission is our best chance at investigating a world that could answer the age-old question, are we alone in the universe? If we find even the smallest signs of life's simple microbes, or perhaps organic molecules, that suggest life processes, it would revolutionize our understanding of life itself. This mission isn't just about Europa, it's about the future of space exploration. If Europa can sustain life, then maybe other moons or planets, even in distant star systems, can too. And that brings us one step closer to understanding our place in the vast cosmos. Potential for life on Europa. Now, let's venture into the realm of possibilities that truly ignites the imagination. Could Europa harbor life? Beneath Europa's frozen crust lies a vast ocean, and that ocean may provide the right conditions for life to exist. But how can something as inhospitable as a cold, icy moon support life? Let's explore. The conditions for life. Life, as we understand it, needs three things: water, energy, and organic molecules. Europa has all of these. Water. Europa's subsurface ocean is believed to be vast, with more water than all of Earth's oceans combined. This is crucial because water is essential for life as we know it. And since the ocean is likely in contact with the moon's rocky mantle, it may support the same kinds of chemical reactions that sustain life near hydrothermal vents in Earth's oceans. Energy. While Europa is far from the sun and its surface temperatures are extremely cold, around -160 degrees Celsius, there's still a source of energy. Tidal forces from Jupiter create heat inside Europa by stretching and squeezing the moon as it orbits the gas giant. This process, called tidal flexing, generates enough internal heat to keep the ocean in liquid form and possibly drive volcanic or hydrothermal activity on the ocean floor. Organic molecules. The building blocks of life, such as carbon, hydrogen, nitrogen, and oxygen, may exist in Europa's ocean, either delivered by comets or produced by chemical reactions between the ocean and the seafloor. While we don't know for sure, the potential presence of organic molecules in Europa's ocean is one of the key things the Europa Clipper mission will investigate. The ecosystem analogy, Earth's hydrothermal vents. One of the best analogies we have for what might exist on Europa comes from Earth's deep-sea hydrothermal vents. These vents are located on the ocean floor, far from sunlight, yet they teem with life. The heat and chemicals released by volcanic activity in these vents support ecosystems that include bacteria, tube worms, and other strange creatures, all thriving without sunlight. Europa's ocean may have similar hydrothermal vents. If these exist, they could provide the energy needed to support life. The organisms on Europa, if they exist, might be simple microbial life forms similar to Earth's extremophiles, organisms that can survive in extreme environments. While we don't expect to find fish or large creatures, even the discovery of microbial life would be one of the most profound discoveries in human history. Europa isn't the only ocean world in the solar system. One of its closest competitors in the search for life is Enceladus, a small moon of Saturn that has captured the attention of scientists for its own subsurface ocean and spectacular water plumes. While Europa and Enceladus share some similarities, there are key differences that make each moon unique and worth exploring in their own right. Europa's thick ice, Enceladus' thinner shell. One of the main differences between Europa and Enceladus is the thickness of their ice shells. Europa's ice layer is estimated to be about 10 to 30 kilometers thick, while Enceladus ice is much thinner, possibly only 1 to 5 kilometers. This thinner shell on Enceladus means its ocean is more easily accessible, and its water plumes erupting from cracks in the ice are easier to study directly. For Europa, the thick ice crust makes exploration more challenging. This is why the Europa Clipper is crucial. It uses advanced instruments like ice-penetrating radar to peer through the ice and determine what lies beneath. Scientists hope that Europa's thick ice may protect its ocean from harmful cosmic radiation, creating a more stable environment for life. Water plumes, the gateway to the ocean. Both moons exhibit water plumes, but they differ in scale and frequency. Enceladus is famous for its constant geysers, which have been observed shooting water vapor, organic molecules, and even small grains of ice into space. The Cassini spacecraft flew through these plumes multiple times, sampling the water and detecting hints of organic molecules, raising the possibility that life could exist in Enceladus ocean. Europa's plumes, on the other hand, are more elusive. Detected by the Hubble Space Telescope, they are thought to be intermittent and smaller than those of Enceladus. But if the Europa Clipper can find and sample these plumes, it could be a game changer. The plumes provide a rare opportunity to analyze Europa's ocean without having to drill through its ice. Europa is larger than Enceladus, with a diameter of 3,100 kilometers, compared to Enceladus' 500 kilometers. This size difference has important implications. Europa's larger mass gives it stronger gravity, which might help maintain a more stable ocean environment over long periods of time. A stable ocean is key for life to develop and thrive. On Enceladus, the weaker gravity and smaller size might mean that its ocean is more affected by external forces, such as Saturn's gravitational pull. This could lead to more dynamic interactions between the ocean and the ice, creating an active environment where life might be supported, but perhaps with more volatility than Europa's ocean. Could humans colonize Europa? Human exploration and even colonization of Europa may seem like science fiction, but it's not entirely out of reach. Europa's surface, while hostile, could one day host robotic stations or even underground habitats protected from Jupiter's intense radiation. These stations could serve as outposts for scientists studying the moon's ocean and any potential life forms. Colonizing Europa presents unique challenges. Its ice-covered surface, harsh radiation environment, and extreme cold would require advanced shielding and sustainable life support systems. But it's not impossible to imagine a future where we send humans to the Jovian system, perhaps using Europa as a stepping stone to explore the outer solar system. Ultimately, the exploration of Europa is about more than just science. It's about our future as a spacefaring civilization. As we look to the stars, moons like Europa will guide our way, offering both challenges and opportunities as we seek to understand the universe and our role within it. And who knows? One day humans may stand on Europa's icy surface, gazing up at the distant sun, knowing that they are not alone in the cosmos. As the Clipper mission probes Europa's icy waters, scientists are also using advanced telescopes to search for signs of life beyond our solar system. The James Webb Space Telescope, JWST, launched in December 2021, has already revolutionized our understanding of distant worlds by allowing astronomers to study the atmospheres of exoplanets in detail. JWST can detect biosignature gases, gases produced by living organisms that accumulate in planetary atmospheres. On Earth, for example, oxygen began accumulating billions of years ago due to photosynthetic bacteria. By detecting such gases like methane, carbon dioxide, JWST offers possible signs of life on exoplanets light years away. One of the most remarkable findings came from its study of the exoplanet WASP-39b, located about 700 light-years away. Using its infrared instruments, JWST detected the presence of carbon dioxide in the planet's atmosphere, a first for an exoplanet. While WASP-39b itself is a gas giant and not suitable for life, this detection demonstrates JWST's ability to analyze atmospheric compositions with unprecedented detail, paving the way for future studies of Earth-like planets. Even more intriguing are the discoveries surrounding K218b, a sub-Neptune-sized exoplanet orbiting in its star's habitable zone. In 2023, JWST observed the planet's atmosphere and found methane and carbon dioxide, both of which are potential biosignatures. It also detected dimethyl sulfide, a molecule often produced by living organisms on Earth, sparking excitement among scientists about the possibility of life-supporting processes occurring on K218b. Beyond atmospheric studies, JWST has uncovered evidence of organic molecules, the essential building blocks of life, in distant star-forming regions like the Prolintulin Nebula and the protoplanetary disk of PDS-70. These findings suggest that the precursors to life may be widely distributed across the universe, increasing the likelihood that life has emerged elsewhere. These specific breakthroughs are just the beginning. As JWST continues to explore the universe, its unparalleled sensitivity and precision promise to reveal even more about the environments where life might exist, bringing us closer to answering the question, are we truly alone? In addition to James Webb Space Telescope, scientists eagerly await the completion of the Giant Magellan Telescope, GMT. Expected to be fully operational within this decade, GMT will offer 10 times the resolution of the Hubble Space Telescope, making it ideal for studying nearby exoplanets. With its unprecedented power, GMT will help scientists detect subtle atmospheric changes on exoplanets and reveal Earth-like worlds in the habitable zones of Sun-like stars. These missions, which extend our reach to the stars, hold the potential to uncover life in the form of alien microbes, biosignature gases, or possibly more advanced life forms. Closer to Earth, researchers continue the decades-long search for intelligent extraterrestrial civilizations through the SETI Institute. SETI's network of radio telescopes scans the skies for radio waves or signals that might indicate technologically advanced civilizations. The Allen Telescope Array in California, a central instrument in SETI's mission, monitors millions of radio channels in search of unique patterns that could signal intelligent life. Although no definitive signals have been detected, the search is ongoing. Every potential signal, no matter how faint, rekindles hope and drives scientists to continue exploring the depths of space for signs of communication from distant civilizations. Meanwhile, the question of why we haven't yet encountered extraterrestrial civilizations, despite the vastness of the universe, remains. Known as the Fermi paradox, this conundrum has inspired theories ranging from the Great Filter hypothesis, which suggests that civilizations may self-destruct before achieving interstellar communication, to ideas that alien civilizations intentionally avoid contact. Yet the sheer scale of the cosmos leaves many scientists confident that life must exist somewhere beyond our small corner of the galaxy. Venus is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles, or 6,052 kilometers, it's approximately 95% the size of Earth. Its mass is about 81.5% that of Earth. This similarity in mass and size means that Venus also has a comparable density to Earth, approximately 5.24 grams per cubic centimeter, implying a similar rock-iron composition. Venus and Earth have a comparable structure, a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as that of Earth, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles or 3,200 kilometers in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center. This is overlaid by a thin crust, estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic among the planets of our solar system. Unlike most other planets, which spin on their axes in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This is a phenomenon that isn't yet fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day, a full rotation on its axis, taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day due to its retrograde rotation and orbit around the Sun. The solar day on Venus is about 116.75 Earth days. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. the surface gravity on Venus is about 90% of the surface gravity on Earth. This means that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with a relatively low number of craters, indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles or 240 kilometers. The planet has far more volcanoes than any other in our solar system. However, there's currently no definitive evidence that these volcanoes are still active, although recent studies suggest that some may have erupted within the last few million years. Despite the apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, 96.5%, with most of the remainder being nitrogen. However, there are also traces of other gases, such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers. The troposphere, extending from the surface to about 40 miles up, the mesosphere, stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere that merges with the void of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, which is hot enough to melt lead. There's very little temperature variation between day and night or between the equator and the poles due to the thick atmosphere's efficient heat distribution. This results in a virtually constant, furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus boasts the highest mountain in the solar system, Maxwell Montes, rising 20 kilometers, about 12 miles above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle and arachnoids, circular structures with a complex pattern of fractures. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists are interested in further exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. Can science fiction become reality? This question isn't just for fans of novels or movies, it's one of humanity's greatest mysteries. The discovery of extraterrestrial life and possibly making first contact would undoubtedly rank as one of the most monumental scientific breakthroughs in history. Yet, the universe seems to act like an enormous wall, putting up countless barriers between us and other potential civilizations. Despite these challenges, we continue to search for answers among the stars. Are we truly alone in the cosmos? Or is intelligent life waiting somewhere out there, just beyond our reach? The Arecibo message, our first attempt. In 1974, something incredible happened. At the Arecibo Observatory in Puerto Rico, we sent a powerful radio message deep into space. This wasn't just a casual hello, it was a carefully crafted message packed with information about Earth, our location, basic biology, and even the structure of our DNA. The message was aimed at a star cluster called M13, located about 25,000 light-years away. If there's intelligent life out there, this was our way of saying, we are here. Are you? It was humanity's first direct attempt to communicate with a possible alien civilization. But here's the catch. Even traveling at the speed of light, that message won't reach its destination for another 25,000 years. And if anyone replies, well, we'll have to wait another 25,000 years to hear back. It's a bold move when you think about it. We're sending out a message with no guarantee that anyone is listening. But it raises the ultimate question. Are we really alone in the universe? Is there life out there? So how likely is it that someone or something is out there waiting for our message? The answer seems obvious, yes. Life on Earth began almost as soon as our planet formed. If it could happen here, why not somewhere else? Astronomer Frank Drake tried to tackle this question with a groundbreaking approach. He created the Drake equation, a formula designed to estimate the number of intelligent civilizations in our galaxy. When the equation was first introduced, scientists projected that there could be about 10,000 civilizations capable of communication. Since then, our understanding of the universe has grown dramatically. For one, we've discovered exoplanets, planets orbiting stars outside our solar system. At last count, astronomers have confirmed over 5,500 exoplanets, and they believe that's just the tip of the iceberg. What's more, scientists now estimate there may be more planets than stars in the cosmos. If the universe is so good at making planets, it stands to reason that it might also create the conditions for life. Even if life is rare, The sheer size of the universe offers countless opportunities for it to exist. The odds seem to favor the idea that intelligent civilizations are out there, somewhere. But here's the mystery: if there's so much potential for life, why haven't we found any evidence yet? The vastness of the cosmos. If the universe is brimming with possibilities for life, then why haven't we found anyone yet? One answer might lie in the sheer size of the cosmos. It's hard to wrap our heads around just how vast everything is. Take our own galaxy, the Milky Way. It's so big that even traveling at the speed of light, a signal sent from one end to the other would take 100,000 years to arrive. We're out here in the suburbs of the galaxy, about 75,000 light years from its edge. That's a long way from any cosmic neighbors. Now think about the Arecibo message. After 45 years, it has only covered a fraction of the distance to its target. At this rate, communication with another civilization becomes a waiting game on a scale we can barely imagine. Even if there are thousands of intelligent civilizations in the galaxy, the distance between us might be so immense that we'll never hear from one another. The laws of physics don't make it easy. Nothing can travel faster than the speed of light. So, no matter how advanced we become, those vast distances are a roadblock we can't get around. But that hasn't stopped us from trying. Projects like Breakthrough Listen are using the most advanced technology on Earth to scan the skies. With radio telescopes and optical sensors, they're focusing on the stars and galaxies closest to us, searching for any signs of intelligent life. So far, it's been quiet, like waiting for a call that never comes. But that doesn't mean no one's out there. It just means we're still looking. The patience of the search. Searching for extraterrestrial life is a bit like looking for a needle in a cosmic haystack. Imagine this: even if there are 10,000 intelligent civilizations in the galaxy, there are roughly 250 billion stars out there. That's like trying to find one specific house in a city of 25 million. It's an enormous challenge, and it's going to take time. Even if we do eventually hear something, there's another problem: time itself. Imagine a civilization sends us a signal, but by the time it reaches us, they're already gone. Civilizations rise and fall, and the timeline of the universe is so vast that we might simply be missing each other. Earth has been around for 4.5 billion years, but humans, we've only been here for about 300,000 years. In cosmic terms, we're late to the party. The universe is 13.8 billion years old, meaning other civilizations could have existed billions of years before us. They might have reached incredible technological heights, only to disappear long before we even began searching. But this doesn't mean we should give up. Our search is just getting started. Breakthrough Listen, for instance, is focusing on the 1,700 stars nearest to us, using cutting-edge technology to catch even the faintest signal. If there's life out there, projects like these are our best hope of finding it. For now, though, we wait. And in the grand timeline of the universe, patience might be the most important tool we have. The Kardashev scale, measuring civilizations. If intelligent civilizations exist, how advanced could they be? To answer this, scientists use something called the Kardashev scale, which ranks civilizations based on their ability to harness energy. Type 1 civilizations can use all the energy available on their home planet. Type 2 civilizations can harness the energy of their entire solar system. Type 3 civilizations are the ultimate powerhouses, capable of using energy from an entire galaxy. And where do we stand? Well, we're not even at Type 1 yet. Humanity is somewhere around Type 0.7, still learning how to fully utilize the energy resources of Earth. But the Kardashev scale offers a glimpse of what might be possible if a civilization survives long enough to keep advancing. Imagine a Type 2 civilization. They might build something like a Dyson sphere, a structure that surrounds a star and captures nearly all of its energy. First proposed by physicist Freeman Dyson, this concept represents technology so advanced it's almost hard to imagine. If such structures exist, they would block most of the star's light, leaving only faint traces of infrared radiation, something we could potentially detect. In 2015, NASA's Wide Field Infrared Survey Explorer scanned the skies, looking at 100,000 galaxies for signs of these advanced civilizations. But they found nothing. Not a single confirmed Dyson sphere. Does this mean Type 2 or Type 3 civilizations don't exist? Not necessarily. They could be too far away, too rare, or using technology we can't even comprehend. The lack of evidence doesn't mean the universe isn't teeming with life, it just means we haven't found it yet. Are we late to the party? The universe is old, 13.8 billion years old to be exact. Civilizations could have risen and fallen long before Earth even formed. It's humbling to think that while humans have been here for about 300,000 years, that's just a blink in the timeline of the cosmos. Some scientists believe this might explain why we haven't made contact yet. It's possible that intelligent civilizations existed billions of years ago, but are now long gone. Imagine a message finally reaching us from another world, only for us to discover that the senders vanished ages ago. It's like trying to join a party only to find out it ended before you even got the invitation. But there's another possibility. What if we're the early ones? Earth may seem ancient to us, but in the grand timeline of the universe, we could be among the first intelligent species to emerge. If that's true, it's not just about waiting for others to contact us, it's about deciding what kind of civilization we want to be. Right now, humanity is at a crossroads. We're building the tools to explore the cosmos, but we're still learning how to take care of our own planet. If we ever hope to reach the levels of a Type 1 or Type 2 civilization, we'll need to survive the challenges of today. Our search for extraterrestrial life is about more than just finding aliens. It's about understanding our place in the universe. Whether we're latecomers to the cosmic party or among the first civilizations to emerge, the quest itself is a testament to human curiosity and resilience. Projects like the Breakthrough Listen initiative remind us that even if the universe is vast and the odds seem impossible, we are determined to keep looking. Every discovery, from exoplanets to radio signals, brings us closer to answering the question, are we alone? But maybe the most important takeaway is this: the universe doesn't owe us answers. The search for intelligent life might take decades, centuries, or even longer. Yet, by exploring the cosmos, we're not just searching for others, we're learning about ourselves. Humanity is still in its infancy on the cosmic scale, but we have the tools and the ambition to grow. One day, we might become the advanced civilization others are searching for. Until then, we'll keep listening to the stars, sending out our messages, and dreaming of the day we finally hear something back. The hypothesis of natural filters in the universe posits that advanced extraterrestrial civilizations may have existed for a long time, but were eradicated by these natural filters. If extraterrestrial life exists, the question arises whether their forms and environments would be similar to those on Earth. This idea draws from the concept that certain conditions, whether astrophysical, biological, or societal, act as filters that limit the emergence and longevity of advanced civilizations. Possible filters include cataclysmic events, astrophysical phenomena, or self-destructive behaviors inherent to intelligent societies. If extraterrestrial life exists, its forms and environments might not necessarily resemble those on Earth. Life could evolve in diverse ways depending on the unique conditions of each planet. The variety of planetary environments and the adaptability of life make it plausible that extraterrestrial beings might have different biochemistries and physical characteristics. Rocky planets like Earth are considered ideal for supporting life due to their specific conditions. However, these planets are delicate and susceptible to various threats. And this fragility means the universe could filter out intelligent life quickly. One significant threat comes from violent stellar events such as gamma-ray bursts, which are powerful enough to sterilize planets over vast cosmic distances, potentially affecting entire galaxies. Even if intelligent species manage to survive these natural occurrences, there is another risk: self-destruction. Drawing from our own experiences on Earth, the development of technology has given us the capability to alter our climate and create weapons of mass destruction. This self-destructive potential poses a serious risk for advanced civilizations. It is plausible that technologically advanced societies may have a brief existence, as evidenced by our own history. The short lifespan of advanced civilizations could be a reason why there are so few observable ones at this point in time. The possibility arises that many civilizations may have emerged, but their existence was short-lived due to self-inflicted challenges. This scarcity of long-lasting civilizations could explain the limited opportunities for communication with extraterrestrial beings. Discovering remnants of an extinct alien civilization could serve as a profound warning for humanity. If we were to find evidence of a civilization that destroyed itself through pollution or conflict, it would be akin to looking at our own potential future. This sobering realization could provide valuable lessons for us on Earth, emphasizing the importance of avoiding similar pitfalls. In our quest for understanding the cosmos, we can only hope that some advanced alien species have managed to navigate the challenges posed by the universe's potentially lethal filters, offering a glimpse of long-term survival and prosperity. If we are lucky, there may be an extraterrestrial civilization that will come to visit us in the future. Imagine making contact with aliens. Sounds cool, right? But hold on, are we assuming too much? We tend to think that aliens are just like us, but here's the twist, they're not. We might be imagining them based on what we know about life on Earth, assuming they live on planets like ours. But guess what? Most of the universe might not follow our life and planet rulebook. So, could extraterrestrials even survive first contact with us and our planet? July 2019, a satellite on a test mission spotted a new alien world named TJ357d about 31 light-years away. This super-Earth is over 6 times heavier than our cozy home planet. Now, what's a super-Earth? A terrestrial planet, but bulked up with more mass. More mass means more gravity, creating a whole different vibe compared to our Earth. Imagine aliens living on a super-Earth. The gravity there could be super strong. They might not be tall, but I bet they'd be super strong. Super-Earths are just one of the many wild things the universe cooks up. Who knows what other surprises are out there? The possibilities are as vast as the cosmos itself. The universe is a vast playground with planets of all shapes and sizes orbiting stars of various types and sizes, forming countless configurations. This diversity opens up a world of possibilities for life that is much richer and more varied than we ever imagined. However, we need to break free from the idea that extraterrestrial life will resemble us. If we're expecting beings with 2 legs like ours, we might as well abandon that notion. The truth is, life out there could be radically different. Consider this scenario. An intelligent alien species in our cosmic neighborhood wants to say hi to us. But here's the catch. If that alien evolved on a super-Earth or circled a red star instead of a yellow one, its biology could be so alien that it might never set foot or tentacle on our planet. Looking at life on Earth, it seems like it's tailor-made for our specific temperature, elements, and environment. Now, imagine an exoplanet with conditions conducive to life. It could still host life forms vastly different from what we're accustomed to. What if an alien world has a bit more potassium, is warmer than our average Earth, or has a thicker atmosphere? Each of these subtle differences could create an entirely distinct ecosystem. So the big question is, can an alien organism truly adapt to our ecosystem when it lands on Earth? It's a cosmic mystery waiting to unfold. From the moment our ancestors first gazed up at the night sky, humanity has been driven by an insatiable curiosity. We've evolved from gathering around campfires to gathering knowledge, transforming the very planet we call home. But as our population swells and our technology reshapes the environment, the question lingers, have we outgrown Earth? It's not just a philosophical query. As we continue to push the boundaries of science and discovery, the next logical step seems to be beyond our atmosphere, towards the stars. The idea of leaving Earth behind and venturing to new worlds isn't just science fiction anymore, it's an inevitable chapter in the story of human progress. We've come a long way, but as the challenges mount, one destination stands out among all others: Mars. A cold, desolate planet, sure, but perhaps the stepping stone we need for our next grand adventure. But can we really live there? Let's dive into why we're even considering the red planet in the first place. When we think about where humanity could establish a new home, Mars often takes center stage. And for good reasons. First, it's relatively close, well, in space terms, at least sitting around 140 million miles away from Earth. That makes it one of our nearest planetary neighbors, a practical choice when considering the logistics of travel and communication. Mars also has a few key features that make it appealing. The planet's day, or sol, is only about 40 minutes longer than a day on Earth, meaning we wouldn't have to drastically adjust our daily rhythms. And while the sunlight Mars receives is less intense, we could still make use of solar power to some extent. Then there's the question of resources. Mars is rich in elements like iron, which gives it that iconic red hue, as well as magnesium and silicon. These materials are crucial for building infrastructure, making it possible for future settlers to rely on what the planet offers, rather than bringing everything from Earth. But perhaps the most exciting possibility is water. Evidence suggests that liquid water once flowed on Mars, and today significant amounts of water are locked up in the planet's ice caps. If we could melt that ice, we could potentially create vast reservoirs of liquid water, a basic ingredient for life as we know it. So, from a practical standpoint, Mars seems like it could be a reasonable target for human exploration. But of course, the question isn't just whether we could go to Mars, but whether we should. Mars may seem promising on the surface, but beneath that allure lies an environment far from welcoming. For starters, the atmosphere is so thin that it barely counts about 1% of Earth's air pressure. In practical terms, if you stepped outside without a suit, the low pressure would cause your blood to boil in seconds, even with liquid water nearby. It's not just a thin atmosphere, it's also composed almost entirely of carbon dioxide. Breathing Mars air would be like trying to breathe in the fumes of a car's exhaust deadly. And if that wasn't enough, Mars also lacks a key feature that makes Earth livable: a protective magnetic field. On Earth, this invisible force shields us from harmful cosmic and solar radiation. Mars, with its weak or absent magnetic field, leaves anyone on the surface exposed to radiation levels 40 to 50 times higher than what we experience here. Over time, this radiation can significantly increase the risk of cancer and other health problems, making long-term exposure a serious concern. The weather on Mars isn't much friendlier either. Mars is notorious for its massive dust storms, which can whip up winds of over 250 miles per hour and last for weeks. Some storms grow so large that they cover the entire planet, blocking out sunlight and damaging equipment or habitats. On top of that, temperatures on Mars are brutally cold. The average temperature is a bone-chilling -62 degrees Celsius, and in winter, it can drop to a frigid -140 degrees Celsius. It's not exactly the kind of place where you'd want to step out for a breath of fresh air or any air. And while Mars' gravity is about 1/3 of Earth's, we still don't fully understand the long-term effects that lower gravity would have on the human body. Astronauts who spend time in space, even for relatively short missions, suffer from muscle loss and weakened bones. On Mars, these issues could be magnified over years, leading to physical deterioration at a much faster rate. In short, life on Mars, at least in its natural state, isn't something we could sustain without serious intervention. Mars may beckon to us, but it does so with the promise of significant hurdles to overcome. Even if we manage to get to Mars, surviving there is another story. The low gravity, thin atmosphere, and intense radiation are just the beginning. The real test of endurance would come from the long-term effects on the human body and mind. Let's start with what happens to the body. Astronauts who spend extended periods in space face significant physical changes, even with rigorous exercise regimens. Without the pull of Earth's gravity, muscles atrophy, and bones lose density. On Mars, where gravity is only a third of what we're used to, these effects would likely accelerate. In time, you might feel more like an elderly person, with weaker muscles and fragile bones, even if you started out healthy. But it's not just the physical toll that's concerning. Living on Mars would mean being confined to small, artificial habitats, cut off from the vast, open spaces of Earth. While that might sound manageable in the short term, over time, such isolation and close quarters with a limited group of people could lead to psychological strain. Researchers have long studied how astronauts cope with the stress of long-duration space missions, and Mars would push those boundaries further. Depression, anxiety, and even interpersonal conflicts could become common in a Martian colony where there's no easy escape from the social dynamics at play. And if you thought farming on Earth had its difficulties, try growing food on a planet where the soil itself is toxic. Martian soil contains high levels of perchlorates, chemicals that are harmful to humans. That means growing crops on Mars isn't as simple as planting seeds in the ground. We'd need to detoxify the soil first or develop other innovative methods like hydroponics to grow food. Without a reliable food source, settlers would be entirely dependent on Earth for shipments, a dangerous reliance given the distance and time involved in space travel. So, while the idea of setting foot on Mars is thrilling, the reality is that survival there would require more than just courage and determination. It would demand cutting-edge technology, medical breakthroughs, and psychological resilience perhaps more than we've ever had to muster before. The idea of transforming Mars into a planet more like Earth, a process known as terraforming, has captivated imaginations for decades. It's a bold concept, envisioning a future where we could warm the planet, thicken its atmosphere, and make the surface habitable. But turning this dream into reality is an enormous challenge, both scientifically and practically. One of the more audacious ideas for kick-starting the process comes from Elon Musk, who has proposed using nuclear weapons to vaporize the polar ice caps on Mars. The theory is that by releasing the carbon dioxide and water stored in these frozen caps, we could create a greenhouse effect, trapping heat and warming the planet. In essence, we would trigger a runaway climate change this time on purpose, but there are major hurdles to this plan. For starters, even acquiring enough nuclear devices to do the job is a monumental task. And beyond that, there's a real risk that this strategy could backfire, causing a nuclear winter on Mars. Instead of warming the planet, we might end up making it colder by blocking out the already scarce sunlight with dust and debris. An alternative approach suggests using giant mirrors in space to focus sunlight on the Martian poles. The idea is to melt the ice caps using concentrated solar energy, gradually warming the planet. However, this too presents a colossal engineering challenge. To generate enough heat, the mirror would need to be about 250 kilometers across, significantly larger than any object we've ever launched into space. Building something of that scale in orbit would require unprecedented advancements in technology and materials. If bombs and mirrors seem a bit far-fetched, another more Earth-inspired solution is the use of greenhouse gases. Specifically, chlorofluorocarbons, CFCs, the same compounds that we banned on Earth for damaging our ozone layer. On Mars, CFCs could be a powerful tool, trapping heat far more effectively than carbon dioxide. We might even be able to produce these gases from materials found on Mars itself. But releasing enough CFCs to warm the planet would take time, and some scientists estimate it could take centuries or even millennia to see a noticeable effect. So, while terraforming Mars may not be impossible, it's certainly a long-term goal, perhaps stretching across generations. It's not something that could be achieved overnight or even within our lifetimes. But the fact that we're seriously considering such ideas shows just how far human ambition can stretch when it comes to exploring new frontiers. If turning the entire planet into a second Earth feels like a distant goal, a more immediate challenge is creating pockets of habitable environments on Mars. Even if we managed to warm the planet, the Martian atmosphere would still be almost entirely carbon dioxide. Breathing would still be impossible without the help of technology. One idea is to tackle the lack of breathable air head-on. NASA has already taken the first steps toward this with a device called MOXIE, which was sent to Mars aboard the Perseverance rover. The MOXIE's job is to convert Martian carbon dioxide into oxygen, much like a tree does on Earth. While MOXIE is just an experiment for now, it demonstrates the possibility of producing oxygen directly on Mars. Scaling this up to supply an entire colony with breathable air, however, is a monumental challenge. The kind of industrial-scale oxygen production we'd need is far beyond our current capabilities. But perhaps the solution isn't to build machines, maybe nature could help. Just as cyanobacteria helped oxygenate Earth's atmosphere billions of years ago, we could theoretically introduce similar microorganisms to Mars. These tiny life forms could gradually convert CO2 into oxygen, slowly transforming the Martian air into something more breathable. It's not science fiction either. This process occurred naturally on Earth, though it took millions of years. On Mars, the timeline would likely be shorter, but still not something we could achieve in just a few decades. Even if we manage to produce enough oxygen, there's another ingredient that's equally crucial: nitrogen. Earth's atmosphere is about 78% nitrogen, which helps to stabilize oxygen levels and make the air breathable. Unfortunately, Mars doesn't have significant amounts of nitrogen, meaning we'd have to import it. One idea is to harvest nitrogen-rich asteroids and crash them into Mars. Another, more futuristic proposal is to transport nitrogen from Saturn's moon Titan, which has a thick nitrogen-rich atmosphere. But these plans are, to say the least, logistically complex and would require an entirely new level of space transportation technology. Beyond breathable air, we would also need protection from the intense solar and cosmic radiation that constantly bombards Mars. On Earth, our magnetic field shields us from these dangers. Mars, however, has no such natural protection. One proposal to solve this involves generating an artificial magnetosphere. Scientists have floated ideas ranging from placing a massive superconducting ring around Mars to installing a magnetic shield between Mars and the Sun. While these concepts are fascinating, they're still very much in the theoretical stage, and implementing them would require engineering feats we have yet to achieve. In short, creating a livable environment on Mars involves more than just a warm climate and breathable air. It's a multifaceted problem that requires solutions from both biology and physics, and could take many decades or even centuries to fully realize. While terraforming Mars and transforming its entire environment sounds like an ambitious long-term goal, there's a more immediate and realistic approach: building artificial habitats. Rather than trying to change the planet itself, why not focus on creating isolated, controlled environments where humans can live and work? These habitats could be constructed on the surface of Mars, designed to shield inhabitants from the planet's many dangers: radiation, dust storms, and extreme temperatures. The idea would be to create domed or enclosed structures complete with life support systems that provide Earth-like conditions inside. We've already tested the basics of this kind of setup with projects like the International Space Station, where astronauts live for months in a fully artificial environment. On Mars, we'd need to scale up those ideas to accommodate larger populations and much longer stays. Another, potentially more secure option is to build habitats below the surface. The Martian soil, called regolith, could be used as a natural shield against harmful radiation and the wild weather patterns on the surface. These underground bases could offer more stability and protection, although they come with their own engineering challenges. Creating tunnels or caverns on Mars would require specialized equipment and techniques that go far beyond anything we've built on Earth. This idea isn't as far-fetched as it might sound. Elon Musk, always at the forefront of space exploration plans, has suggested building a fully functioning Mars city with a population of up to 1 million people by 2050. While this timeline may be optimistic, it speaks to the growing interest in colonizing the Red Planet. However, even with Musk's ambitious plans, the costs involved are staggering. Estimates put the price tag at around $10 trillion, roughly 10% of the world's combined GDP. In these habitats, everything from oxygen production to waste recycling would have to be handled efficiently. Hydroponic systems could be used to grow food indoors, avoiding the toxic Martian soil. Energy could come from solar panels or nuclear power, both of which are well suited for space missions. In many ways, these habitats would be like miniature versions of Earth, carefully engineered to sustain human life in the most extreme of environments. While the idea of living in a bubble on another planet may not be as romantic as strolling through a fully terraformed Mars, it's one of the most viable options we have for making life on the Red Planet a reality, at least for the foreseeable future. Mars is, without a doubt, the most feasible candidate for human colonization beyond Earth. Yet whether through building vast artificial habitats or attempting to terraform an entire planet, the obstacles are immense. Creating a livable environment on a world so far removed from what we're used to will require decades, if not centuries, of technological advancements and global collaboration. It's a race against time, one that runs parallel to the pressing issues we face here on Earth, from climate change to resource scarcity. The question then isn't just about whether we can go to Mars, but whether we will. Will humanity band together to make this dream a reality before the forces of nature or our own actions make such a mission impossible? Will we conquer the stars before we're undone by pandemics, natural disasters, or other unforeseen threats? The future is uncertain, but one thing remains constant: our desire to explore, to push boundaries, and to seek out new frontiers. As we gaze toward the stars, Mars is not just a destination, it's a symbol of our relentless drive to explore the unknown. Whether the next chapter in human history takes place on the Red Planet, or we continue to face the challenges of Earth, the spirit of exploration that has carried us this far will undoubtedly continue to shape our future. Everything we know represents just 5% of the universe. What is the rest? Normal matter protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions: length, width, and height, and 1 dimension of time, making a total of 4 dimensions in spacetime. This is known as the 4-dimensional spacetime. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions. But these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the 4-dimensional spacetime can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence? Or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the theory of Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past, through the present, and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the spacetime continuum, which is the four-dimensional fabric of the universe, consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness, in a closed system tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature. In certain situations, 2 particles can seemingly be in instant connection with each other, even if they are located at opposite ends of the universe. The phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no-communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare? Or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is, because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us, because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes, that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics as we know them break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in space-time. However, there is no direct evidence to suggest that wormholes exist either.